Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 19 in the course Advanced Robotics. In the last class we were talking about sensors, and I explained the various kind of sensors which are there, internal sensors and a few external sensors. Today we'll move on to the next topic, which is actuators. We started off briefly about actuators in the last class where I talked about stepper motors. So today I'll continue my discussion from stepper motors and then look at the various kinds of other actuators which are there. And after that we'll move on to basic control systems. So in control systems, we'll see how using a sensor actuator, we can design a controller which can actually take the robot link or the end effector of the robot from one point to another point, or we can make the end effector, or we can make a robotic system perform a task. Okay, so today we'll continue our discussion on actuators. In the last class, we looked at the various kind of actuators which are there, and we can very briefly classify actuators as electrical actuators, pneumatic actuators, hydraulic and advanced actuators. And in the last class I explained that depending on the kind of torque that is required, you can use either electrical, pneumatic or hydraulic. Hydraulic is the strongest, which gives you the maximum power output, and industrial manipulators which carry very heavy loads like 50 kg, 100 kg. Very often the base link of the robot is actuated by hydraulic actuators. The most common is electrical actuators, because of the very simple reason that a motor is easy to control, and in the end effector, the gripper, we normally have pneumatic actuators which are actuated by piston cylinder mechanism, and this works by air pressure. Okay, now if you go to the micro scale, or the nanoscale, then our normal electrical, pneumatic and hydraulic actuators may not be able to perform the task. So in such cases, we move on to other kind of actuators which are called ultrasonic motors, artificial muscles or molecular motors. So in the last class, we started our discussion with stepper motors. So what I'll do is basically we'll start off with electrical motors, look at stepper motors, DC servo motors. Then we'll go to pneumatic and hydraulic, which are basically piston cylinder mechanisms. And then we'll look at advanced actuators like ultrasonic motors, artificial muscles, etc. So the stepper motors I discussed in the last class. I'll very quickly revise. So the stepper motors, as the name indicates, moves in steps, and how these motors work is explained by the internal construction. So the rotor of the motor has a number of teeth, and these are the teeth of the motors, like 1, 2, 3, 4, they are numbered. And the stator, which is this part, also has coils which are wrapped around the various projections, okay, as shown here. So this is the stator and this is the rotor, and how it works is basically we energize each of the coils in a particular sequence. So if I energize this coil, what would happen is it will generate a magnetic field, and this magnetic field will have a north-south. This will induce a magnetic field on the rotor, because the rotor is either a permanent magnet or it's a ferromagnetic material. So it's either permanent magnet or it's a ferromagnet. It's made up of ferromagnetic materials. So when a magnetic field is created by the coil, a magnetic field is induced in this rotor, and if you have a north-south here, we'll have a north-south here. So what will happen, this north will get attracted to that south, and this teeth will move in that direction and get aligned with the pole B. So if I actuate B, then what will happen, 6 will move and align with pole B. Then if I actuate C, then this number 5 will actuate and go that side. And then if I actuate D and then A, what will happen, this will rotate, and ultimately you have a clockwise rotation. As shown in this 4 figures, this is actuated. So this, you can see that the corresponding pole number 6 has aligned with the pole B. Okay, then I'm going to actuate C. Then once you actuate C, what will happen, this pole will go here, then actuate D, so this will go here, then actuate this one, then this goes here. So you can see that this is number 1, number 2, number 3 and number 4. What has happened here is pole number 3 has got aligned with this 5th coil. Okay, so what has happened, it has rotated clockwise by a number of steps. Now the steps can be of 1.8 degrees normally, And you can have micro steps, micro stepping. Now, how micro stepping is done is if you put or apply different voltages to these two coils in some ratio. Say V1 by V2 has some ratio which is A. So if V1 is greater than V2, then this teeth will go and stop somewhere in between, but more towards V1. Okay. So by controlling this ratio of V1 by V2, we can position the poles somewhere in between here also in micro steps. And in micro steps, they can go up to very, very small steps. Say 0.1 degree it is possible to go with a micro stepping motor. The advantages and disadvantages of stepper motors is that advantage is that they have very high torque. Okay. The number 2, they are easy to control. Number 3 is they are cheap. So you can get in 500 or 600 rupees, you can get a good stepper motor. But the disadvantage is that they are open loop devices, which means that they are not very accurate because they are open loop. This is not in closed loop. You give a pulse and it will rotate by one step. Now, if it has not rotated by one step, you don't know. There is no way of finding out because it's not a closed loop device. So open loop device, then it picks up noise, not accurate. And the worst problem here is that it's very heavy. And because it is very heavy, you cannot put a stepper motor at the end of a manipulator. So if you design a manipulator something like this, okay, so I have a manipulator, I'm designing different links like this, and I put a stepper motor here. If it's very heavy, say these are very, very heavy, so they can be like 2 kg. So what would happen? Immediately there is a very high torque which is required to be supported by this motor now. So you cannot put stepper motors here. At best, you can put it on the base. Okay. So because of these disadvantages, stepper motors are not used in industrial robotics. But for doing small experiments, and if you're going to use the stepper motor in the base, which is not really carrying the weight, in that case, you can use a stepper motor. Advantages, of course, are high torque, easy to control, very cheap. Disadvantage are it's open loop device, it's noise, it picks up noise from other signals, other disturbances around it, and it is not accurate and it's very heavy. These are the disadvantages of the stepper motor. We can have even more powerful stepper motors, which are called mega torque motors. Now, this mega torque motors, in the previous case, if you remember, the rotor had one set of teeth, so one set here. But in this case, in the mega torque motor, there are 2 sets of teeth. So one on this side, one on the other side. Okay, so one on this side and one on this side now. Okay, because of which the torque that is being applied, that can be applied with this motor, is much higher than the single tooth stepper motors. We can also have linear stepper motors. So working principle is exactly same. So we actuate this coils. So I actuate this one first. So what happens? This gets attracted. Then I actuate number 4. So what will happen is 4 will get attracted this side. Then I'll actuate number 3. So what will happen? This will get attracted this side. So as a result of which you see that this one is moved in this direction, right? So by sequentially activating these coils, okay, we can make the rotor. Well, it's not a rotor; it's a linear device. So we can make it translate in that direction. Okay, these are called linear stepper motors. Now, basic working of a DC motor also we discussed in the last class. So a DC motor can be used as a motor. It can also be used as a sensor. Okay. Now, the basic working of a DC motor is that we give it a voltage, so plus minus voltage. What would happen is there is a current that is going to flow in the conductor, and this is going to generate a EMF. Okay, and there will be a corresponding magnetic field associated with that. Now, so this is my rotor. Now, in the stator, okay, we have north-south, and there is already a magnetic lines of force which are going like this. So the magnetic lines of force generated by the coil will start interacting with this magnetic lines of force of the stator, and there will be a resultant torque about this axis. So if this is my axis, there will be a resultant torque depending on the direction of the voltage. Okay, and when this is rotating, what would happen is we need to change this because it is rotating. So what we need is a commutator with and in this commutator, what happens is this rotates and comes this side. So let me explain this. So there is a brush here, and there's half the commutator ring like this, and there is the other half of the commutator ring which is this side. Okay, there's a brush which is in contact here. Okay, so the plus minus is coming from there. So when this is rotating, what is happening? There is a cut in here. So this is a slip ring basically. So when it rotates, this side will rotate and go that side, and this side will rotate and come this side. So the polarity is changing. Okay. Now because of this brush, what is happening, there is contact here, and after some time, after a lot of rotations, what will happen, because of wear and tear, the brush is going to wear off. So brush wear out. Okay, the brush will wear out and you'll have to change the brush. Number two is, because of this, there is friction, okay, at this contact point. And number three is there is chance of spark, etc. Okay, because there is contact which is being made and broken, so there is a chance of small spark at times. Now because of which the DC motor is very cheap, okay, and controlling it is easier. However, because of these problems of brush wear out, friction, spark, etc., it is not used in industrial applications. So if you look at the speed versus, so this is my speed and this is the voltage characteristic. It should theoretically be a straight line, but because of the voltage, there will be some drop here. It will not be exactly a straight line. It will be a little bit like this, then straight and then out. So this part is like this, essentially because of friction, okay, between the slip ring and the brush. Okay. Now because of these reasons, mainly because the brush wears out after some time and you have to replace the brush. So as I was saying in the previous class, that an industrial robot needs to have a life of almost like 5 years. So it is 24 hours a day into 365 days into 5 years. They have to guarantee that much of operation. So it's not a good idea to put this motor, because although it is cheap, it is not very accurate, and because of the friction which is there between the brush and the commutator ring, and also because if the brush wears out, you have to change the brush, you have to open the robot, and all kinds of other problems are there, because of which this is not used. Okay. Now, so this is used in the case of simple experiments. Okay, when we are doing research or doing building simple devices, cheap devices to do experiments, it's okay. Now, so in industrial robotics applications, what is used is a brushless DC motor. As the name indicates, this is a brushless device, which means there is no brush. Okay, so if there is no brush, how is the commutation being done? So that is something that should come to your mind. So here we are doing a commutation, which is basically shown here, which I had drawn here. So this is a commutation. So the plus minus voltage is changing, okay, when it is rotating. So how is this commutation being done when there is no brush or there is no commutator at all? Okay, so how that is done? So this is a brush type motor, in which we have the rotor which is inside, and this contains the coils, and on the outside this is the permanent magnets which are on the outside. Okay, this is a cross section of the motor. This is a normal brush type DC motor. In the brushless DC motor, you can see that the construction is reversed. Okay, here the coils were inside, now here the coils are outside in the stator. Okay, and the permanent magnet has gone inside and the rotor. Okay, so the construction wise they are different. Now what is the difference? Number one is the rotor is light. Okay, it is lighter, whereas here the rotor is heavy. Okay, because there are so many coils and there is a ferromagnetic material on which it is mounted. So the rotor is very heavy in a brush motor, and if it is very heavy, then you can imagine that it's very difficult to control. Why? Because the motor would be rotating at very high speed, say maybe 3000 rpm. So if you want to brake the motor and reverse direction, or you want to control at that speed, it's very difficult. Okay, whereas in the case of the brushless motor, the rotor is inside, so it has low inertia, it has low J. Okay, it has low inertia. Now because it has low inertia, control of the motor, braking of the motor is much easier. Okay, second of all, so rotor is light, so control is easy. Okay, number two is there is no brush. Okay, now if there is no brush, how is the commutation being done? How does it know which polarity to switch in terms of the in the stator coils? It has to change the polarity, right, because it's rotating. So what is done is there are three Hall effect sensors. So there is one here, and one here, and this Hall effect sensor sends the magnetic fields as it is moving. So when this motor is rotating, basically we can sense the speed of the motor based on how the magnetic lines of force are cutting the Hall effect sensors. Okay, and based on that you can do commutation, electronic commutation, and that is exactly how commutation is done here. Now the advantage is there is no brush, rotor is light, so control is easy. Okay, so these are the advantages. Okay. Disadvantage. So disadvantage is that because you need to have magnets in rotor, the magnets have to be very, very strong, because tau is equal to J into theta double dot. Okay, so the torque produced by the motor is equal to J, which is the inertia, into the acceleration. Okay, so if J is very, very low, because we said that it's a very light motor, okay, but it has to be very strong, which means that the magnetic lines of magnetic flux, okay, phi must be high, must be very high. So it basically means that you need very strong permanent magnets. Okay, so if your magnetic lines of flux is very high, only then you can produce a higher torque. Okay, because J is low, so anyway this J is low, so its inertia is low, which is good in terms of control, but is bad in the sense that if your magnetic lines of flux are low, then what would happen is the motor would not produce very high torque. So you need very high torque, but you need very low weights. Okay, so if you want very high torque and very low weight, these magnets are special magnets, which are basically made using using powder metallurgy, and these are basically special magnets. Okay, and that is what adds to the cost. So disadvantage is magnets in rotor, they are very expensive. Okay, number 2 is you need very strong magnetic field. Number 3 is electronic commutation. Now to do electronic commutation, you must have Hall effect sensors, plus there must be electronics, which is actually sensing and actually actuating, changing the polarity of the coils. Because of this, DC brushless motors are very, very expensive compared to brush motors. How expensive? A DC brush motor may cost you 500 rupees, whereas exactly the same motor, if it is brushless, it will cost you 5,000 rupees or maybe higher than that. So there's 10 to 15 times price difference. But because there are no brushes, they are very high speed, control is easier. Industrial robots use brushless motors, okay, because they cannot use brush motors. So most automation devices like NC machines, CNC machines, then motor robots, they all use brushless DC motors. Okay. Now another term which we need to look at is this servo motor. So when we're using a DC motor in a closed loop device, we call it not in a closed loop device, in a closed loop feedback control system. So we have a controller, we have a motor, we have the link, then there is a position sensor. This is my position sensor. So this is a closed loop control system. So a DC motor used in a position control system, closed loop control system, is called a servo motor. Okay, this is called a servo motor. Okay, so very often we use this word servo motor. What it basically means is that it's a DC motor which is being used in a closed loop control system. Okay, now some of these motors are readily available. Okay, some of these motors are this is a special type of motor which has a DC motor. It has a gearbox, a potentiometer, and it has a control structure, control circuit. So basically a PID controller right inside, and all of this is housed in a motor, and these are basically called servo motors, which are sold very openly these days. Okay, so the advantage of this is that there is a DC motor, there is a gearbox and a potentiometer, and the controller is put inside a box, and you can buy this motors, and they are basically called servo motors. So what you can do is you can connect the link output here. So this is my link, I just connect it with screws, and you can make this rotate in a particular direction. Now the motors are calibrated. They normally rotate from 0 degrees to 180 degrees or 270 degrees, and we can control them using PWM, pulse width modulation. So simply by changing the pulse width, the width of this pulse, okay, so this is my pulse width. So by changing that width, when the width is 0, maybe it will correspond to 0 degrees. If the width is full pulse, then it will correspond to 180 degrees or 270 degrees. Okay, and by doing that, you can very easily control the position of this link. So these motors are called servo motors, and they're very easily available, and they're very extensively used by students and even for research. Okay, although they're not used in industries, but these are very interesting motors because you don't have to build a control system yourself. Okay, it is already there. The controller is there, DC motor is there, gear is there, potentiometer is there. Okay, and you can get fairly high accuracy with this kind of system. So a lot of students, research scholars, they build their own automation systems, simple robots, by using this kind of servo motors. So this is basically showing you the various, so it looks like this, a black box. Let me just, it's a black box. So there's a base of the box in which there is the controller, the chip which is having the PID controller. We'll come to that shortly when we talk of control systems. So PID controller is already put in there. And then there is a potentiometer. There is a DC motor which is controlled by the PID controller. This is a closed loop control system. So there is a potentiometer which is giving position feedback. What is the position of the motor? Okay. And the potentiometer is connected to the gear. So there is a top cover on this. And then one output is the potentiometer, the other is the motor shaft. So to connect the potentiometer with the motor shaft, what is done, a gear is put, and then this is the output of the gearbox. So that is the potentiometer connection, which is connecting the so this is the gearbox, and the final output of the gearbox is the shaft on which the final link is put. So you can attach your link here and then control the motor. So this motor has a sensor, it has a controller, it has an actuator, and it is pre-calibrated. So it's very easy to control the position of a link simply by using this servo motor. These are very cheap. They cost about 500 rupees to about 2,000-3,000 rupees. They are pretty good because you can very easily control a DC motor by using one of this. Okay. Otherwise, you'd have to build the whole control structure yourself, which is not very easy. Okay. So the next is, so these are servo motors we talked about. The next is pneumatic actuators, and pneumatic or hydraulic actuators basically are piston cylinder mechanisms. So you have a piston and a cylinder, and air or oil would be input. Maybe we are going to input oil or air from here, and what will happen is this piston will move on this direction, on this side. Again, if I put oil from this side, then what will happen? The piston will move on this side. Okay, now you can have directional control by using directional control valves like this. So this controls which direction the air is going and how much air is going. So you can control the relative position of the piston by controlling the airflow and by using this kind of direction control valves. So this is a pneumatic actuator, and the hydraulic actuator is essentially the same. It's a piston cylinder mechanism only. Okay, and these are mainly used in the grippers, okay, of the robot. Now, now we talked about the size effect, in which we said that if you want to build a very small robot, how small is small? Maybe 10 millimeters or even smaller, 5 millimeters. In that case, you'll need to use actuators which are very small in size. Now, if you make a DC motor which is very small, it will not work. Why? Because the magnetic flux will not be much, and it'll be very, very small. Okay. So if the strength of the magnetic flux is low, then what happens is that the motor will not be able to provide enough torque to move the links. So in that case, we need to move to some other kind of actuator. And these are basically called advanced actuators. They are small, low power consumption, and they support micromotion. These are some of the advanced actuators. The first one is an ultrasonic motor. They are used for micro robotics, cameras, micromotion devices. Artificial muscles used for prosthetics, bioapplications. Molecular motors used for bioapplications. Now, a lot of these applications are already there, and you might have seen them, although without realizing that it's a smart actuator which is there actually. So the first one is an ultrasonic motor, and I'm sure you have used this. And if you have not used it, please, after this class and you understand where it is used, please have a look. Now, where this is used is in cameras, for example. Let me just explain how it works. So unlike a normal brush motor, DC motor, or a brushless motor, or a stepper motor, how this works is we have this is my rotor, this is my stator. Okay, so this is my stator, it's already written here, stator. Now the stator has teeth like this. Okay, and these teeth are basically piezo material, piezoelectric material. Okay. Now piezoelectric material means that if I give it a charge, if I give plus charge, it will expand. Okay, and if I give it some pressure, a charge will be developed there. So if I give it a charge in a particular sequence, what will happen is, if I give a charge here, this will expand a little bit, then I give a charge here, it will expand here, then I give a charge here, it will expand here. Now there is physical contact between this and this, if you can see here. So the rotor and the stator are in physical contact. Okay, and there is friction between them. So if I give a charge here, it's like giving a small kick here. So I give a charge here, it expands. So it gives a small kick there, it gives a small kick there. Okay, so the small kicks will ensure that the rotor is moving in that direction. Okay, this is how it works. Now if you look inside a ultrasonic motor which is used in the cameras, I'm not sure if you look at the if you have seen SLR, the large SLR cameras. So you have this camera body here and you have the very big lens. Okay, you must have seen this, the SLR cameras. So in the SLR cameras there is an autofocus and the lens moves by itself. Okay, for focusing. How does it move? Is there a motor inside? How is it? What is actuating? So there are these ultrasonic motors. On one side, on the body of the camera, this is fixed. So this is my stator. And on the lens side, the rotor is fixed. This is my rotor. Okay, and the operation is, you can see that there are teeth there. And the actuation is exactly the way it is done here. One teeth is actuated at a time, and this will move slowly in that direction. Now this is used in SLR cameras. They also use in digital cameras, digital autofocus cameras, wherever the lens moves. Okay, so you might have seen cameras where the lens, so you have a camera here and the lens moves out, in or out to focus. So all of these digital cameras, to focus the lens motion, focus lens, the motion is provided by this ultrasonic camera, ultrasonic motors. Now this is a piezoelectric material, so it is independent of size. You can make it very small and it will still work. So you can have these ultrasonic motors which are very small in size. So the cameras that are the motors that are placed inside the camera, they are very small in size, but they are very strong. So they are small in size, okay, but they are very strong, very high torque. Okay, they have very high torque because there is physical contact between the rotor and the stator. So they can provide you good torque, but the size is very small, and they are not very expensive. So they are pretty cheap motors. Okay, this is what has ensured that these ultrasonic motors are used in cameras. They're used in many motion devices. Now, the second type of actuators are called electroactive polymers, and how they function is that these are polymers. So a polymer, water-soluble polymers. Now inside the polymer there are plus and minus charges. Okay, plus and minus charges, and on top there is an electrode layer which is put. So there is an electrode layer which is deposited. It can be gold or it can be platinum. Okay, now there are this plus and minus charges inside. So if I give a particular potential, say for example here, I'm connecting it to the plus and a minus. So what is happening? All the plus are moving in that direction. So this is the case where voltage is equal to 0. So in this case you have plus and minus, and they are distributed in the body of the polymer. But the moment I give a potential difference, the plus charges move on that side. Okay, now if the plus charges move on this side, what happens? The pressure gradient this side increases. If the pressure gradient increases, it bends like this. Okay. Now if I reverse the polarity, you see here what is happening. The plus is moving this side now. So this gradient is increasing, is moving on the other side. So simply by changing the polarity, okay, the potential that I'm applying, I can make this bend in a particular direction. And that is how we basically make, and that is how this electroactive polymers work. That by giving a voltage, you can make this bend in a particular direction. Now, in terms of the size effect, these are polymers and you can cut them and make them very small. So if you make them very small, they will still work. Okay, they are independent of the size effect. So number one is they can be made small. and they are water soluble. They can work in water. Okay, so they can work in water because they are water based. Okay, so here there is water inside, so they can work in underwater, say like fish or swimming applications. Okay, or octopus, jellyfish, you can make using these devices because they can work inside water. And number 3 is they are biocompatible. Okay, so they can be made biocompatible also. Okay, so these are called electroactive polymers, are sometimes called artificial muscles. And they behave like muscles. That's where the name artificial muscle comes from. And there are a lot of devices which have been made. The disadvantage of this is that they are not very strong because they are polymers, so they are not very strong. They cannot produce very high torque, but they can produce very high deflection. Okay, now this is an example of an electroactive polymer. So this is a hand which is made of it has 5 fingers, and these are electroactive polymers. Now you can see there is no joint and there is no linkage. Simply by changing the voltage to the fingers, you can make the fingers bend in one direction, and reversing the voltage, they go in the other direction. Okay, this is what we also call as smart actuators and smart sensors, because they work both ways. Okay, now these are, in terms of material, they are ionic polymer metal composites. They are called IPMC, and the material is a Nafion 117, and electrode is platinum or gold, and this is made by electrolysis. The electrodes are made by electrolysis. Now, working mechanism, let's not worry too much about that. Now, what is important is that when we are talking about normal applications, okay, we use brushless DC motors for actuation. Okay, that is industrial applications, industrial automation, this is used. But if you're looking at special applications, okay, say micro, nano applications, or very small applications, then we cannot use BLDC motors anymore. We have to choose some other kind of motor. Now in that case, you'll have to choose an actuator which is normally smart. Okay, that would mean smart material based actuators or IPMC based actuators. So in such cases, we need to worry about the displacement versus the force requirement. Okay, so one is the displacement versus the force generation capacity. What do I mean by this? Suppose I have a cantilever beam. Now if you want that a very high force should be generated from here, okay, that is your force generation capacity, or you want that it is going to bend completely like this, now that's your displacement capacity. So how much it is going to displace and how much it is going to, and what is the force capacity. For example, in a piezo crystal like this, you can give it a charge, it will expand, but the expansion is very, very small, but it produces a very high force. Okay, force is high but displacement is low. Whereas in the case of IPMC, ionic polymer metal composite, the displacement is high but the force is low. Okay, so you need to have a balance between these two, and depending on your application, you can choose which one is it that you want. So this is basically giving us a comparison of different smart actuators. So for example, ionic polymer metal composite on this side, shape memory alloy is here, and electroactive ceramic is on the other side. So these are piezos. Okay, so if you look at the actuation displacement, electroactive polymer, the displacement is very, very high, whereas for piezos it is only 0.1% of the size of the crystal. Okay, that means it hardly has any displacement, whereas force here is about 10 and here it is 40, which is much, much higher. So electroactive polymers have high force but low displacement. Reaction speeds, density, driving voltage, here it is 4 volts, or here it is like 50 to 800 volts. Okay, so this basically gives us a comparison of the different smart actuators which are available, and depending on your application, you need to choose. For example, if you're making a jellyfish or a fish which has to swim underwater, you need very large displacements, but the force could be low. In that case, electroactive polymer will do. Whereas if you want to produce a very high force, you want to push an object with very high force, but your displacement is not high. In that case, electroactive ceramic will do. Okay, so depending on what is your application, if you're somewhere in between, then you're here. Then you can talk about SMIs. So depending on your application, this table is important to know to show that what type of actuator should you choose. Okay, so we stop our discussion on actuators here and move on to the next topic, which is basically control systems. So we'll talk of basic control systems. Why the word basic? Is because control system is a subject in itself. Okay, so there are degrees in control systems and there are institutes in control systems. So control system is a subject in itself. So we'll be covering only the basics of control systems and not go into too much of detail. Just how much we require, that's about it. Okay, so if you look at the basic definitions of control systems, when we say system, so there are three things here. One is control, the other is system. So a system is essentially an interconnection of elements and devices for a desired purpose. That is the definition of a system. An interconnection of elements and devices for a desired purpose. Okay, that is the definition of a system. Now, a control system definition is a system is interconnection of components or a system that will provide a desired response. Okay, so the definition of a control system is finding out the suitable input to get a desired output. Okay, so what is a control system? So first of all, it's a system, and when you're saying control, or rather let me use the word control, what is it that it means? It basically means that you find out a suitable input to get a desired output. Okay, so control basically means finding a suitable input to get a desired output. In the case of a motor, let me take an example. This is a motor and I fixed it to a link like this, and I give it a voltage input V. So how much voltage should I give to make this fellow rotate with a particular velocity? That is a control system problem. So the controller will try to find out what is the suitable input, in this case is voltage, to get a desired output. Say for example, I want 100 RPM. So how much voltage should I give to get 100 RPM? That is a control system problem. Okay. Now a process, this is a general definition. It can be a device, plant, or a system which is under control. Okay. In our case, we will be talking about a robot as our system. Now we talked about open loop and closed loop. In the open loop control system, we have some input. So this is called an input and that is called an output. Okay, and you have the actuating device and you have the process itself. Okay, so I give some input if I consider this to be a motor. I give some voltage and I get some RPM. Okay, so this is an open loop system. There is no feedback coming from the RPM or how much is the speed of the motor coming back to the input side. In a closed loop system, in a closed loop control system, you have a closed loop, which is there is a feedback, and this feedback is basically giving the input to the controller that what is the present position of the. So this is my theta out, this is the output, and this is my theta in. So this is a comparator which is comparing theta in and theta out. For example, theta in I wanted 10 degrees. So theta out, it is comparing what is the present theta, and this comparator is comparing theta in minus theta out. Okay, and then taking some corrective action, parsing it here. Okay, so this is a closed loop control system. So this you can imagine theta in is the link. So let me say not theta in, this theta desired. Okay, so this is the desired theta, let's say 10 degrees, and theta out is this. So what this one is doing is theta desired minus theta out, finding out an error, putting the error here to the controller. The controller is probably multiplying the error with some gain k, okay, and then giving it to the motor. The motor is rotating, and that is how my closed loop control is working. Okay, so this is a closed loop control, but please note that this is for a single link only. And when I talked about sensors and actuators, I talked about independent joint control. That means there is one control loop for each joint and they are not connected with one another. It is like they are all independent. But in reality, we have seen that the dynamic equation is written as the inertia matrix into acceleration plus Coriolis centrifugal forces plus gravity forces. Okay, and this is a nonlinear differential equation. Okay, it's a coupled nonlinear differential equation. Coupled because we know that every joint affects the other joint. We have seen in terms of the propagation of the velocity and acceleration from the base link to the forward link. That means the previous links are affecting the next links. Okay, so when we are making this assumption of independent joint control, this is not really correct. Okay, but it's an assumption, it's a simplification. So the one that is really happening is a multi-input, multi-output system. That is this one now. So in this case, it's a closed loop control system, single input, single output. We also call it seesaw system as single input, single output system. Okay, but in reality, it is a multi-variable control or a MIMO system. So this is a multi-input, multi-output system. What are the various inputs which are going? There are accelerations, position and velocities of all the links which are going, because each one is affecting the other one. Okay, so you have multiple inputs coming in. There is a controller, there is a process, and there is multiple feedback again. So this is what we call a MIMO system. So in reality, the robot control system is a MIMO system. But when we study, we'll study this as a seesaw system. Why a seesaw system? Because it's an assumption and it's simple to understand. MIMO systems are complex systems, and on top of that, this is a nonlinear MIMO system. So it makes it extremely complex to control. And that is the reason why robot control is exceptionally difficult. Okay, and there are very few companies in the world which make robots, industrial robots. And if you ever tried making a robot controller and trying to control it, you'll find that it doesn't work. Okay, essentially because we are trying to control it this way, but in reality it is like this. Okay, as we go along, we'll see that what does the dynamics do, why is it difficult to control, what is the disturbance rejection, things like that. Okay, very brief history of control systems. So some of the earliest controllers were developed very, very long time ago, right in say 300-400 BC. So that old. So control system is nothing new. Okay, it has been going on for very long, and it's there everywhere. For example, if you look in the water level controller, so if you look at the water level controller in the flush tanks, in the bathrooms, so in the bathrooms or in the washrooms, if you look at the how the level of water in the tank is controlled. So this is showing a basic water control system in which you have the water inlet, which is shown here. So water comes in from here, and there is a valve which is controlled, which is connected to this float. So this float is a ball filled with air. You might have seen in the tanks. If you just look and remove the cover of a tank and see you can see this ball, and it is floating. So depending on the level of liquid there, this will be moving up or down. Okay, and if it is moving up or down, this lever will move like this, or it will move like that. So if it is going like this or like this, it is opening or closing that tap there or the valve. Okay, so you can set a particular level of water that you want, and automatically that will be set by the float. Okay, and in the as I just wrote, the water level control in flush tanks, in the bathrooms, and all work on this float governor. So this is called a float regulator mechanism or a float governor mechanism. Working principle is very, very simple. So in this case, what are you controlling? You're controlling the height. How are you controlling the height? The height is being controlled by the height of this float, and this is opening or closing the valve. Okay, and this is letting water in or letting water out. Okay, not letting water out, but either closing the valve or opening the valve, which is controlling the height of the water in there. The other simple example is the Watt's flywheel governor for the steam engines. So how the steam engine works is that there is a piston cylinder. This is the engine, which is the piston cylinder mechanism, right? So in order to make it go faster, you need to pump in more steam. Okay, So to control the steam flow rate, what is done is, you can see that this is the piston which is connected to the crank and is connected to the wheel. So when the wheel rotates about this axis, it is connected to the output shaft, and then it is connected to this bevel gear mechanism. So when this rotates, what happens, these balls which are there, the spheres, they will start, when this is spinning because of centrifugal forces, the faster it spins, this will start moving more in that direction, like that. Okay, and then finally at high spins it will become like this. Okay, so the position of these spheres are controlled by the speed of the engine now. Okay, so how fast this engine is, this wheel is rotating, will depend on the position, relative position of the spheres. So if it is rotating slowly, the spheres will be, this will move up and the spheres will be here, like that. If it is rotating very fast, the spheres will tend to come close together. This will come close together, it will become like that. Okay, so what is being done is that the position of the spheres here, that is shown, that is connected here, is connected to this lever, and there is a fulcrum there, and it's connected to the valve of the boiler, which is letting in the steam. So if the speed is low, what is happening is these spheres will come like this, closer towards the center. Okay, and what will happen, the valve will open. If the valve opens, more steam will get into this engine, and this will start going faster. If it goes too fast again, the spheres will start going outwards like that. So what will happen, this will go up, and if this goes up, what will happen, this valve will close. So you can control the speed of an engine, a steam engine, the early steam engines, by using this governor mechanism. There is no electronics here. It is basically based on physics. Okay. Now these are early examples of control systems which are not really electronic, but they are controls. They are controlling something. Now, how does the controller actually work? There is a desired output that we give. This is called a comparator. Okay, and we take the desired input. Let's call it theta desired. There's an output theta out. Okay, and what the comparator does is it takes theta desired minus theta out, finds the difference, and calls it an error, E. Now this E is multiplied by gains, which is the function of the controller. So the controller can do Kp into E plus Kd into E dot. Okay, this is called a PD controller, and give it to the process. In our process, there is a robot. The robot is actuated by motors. We will say that we are actuating this by motors. So essentially, if there is a motor here, there is voltage which is coming to the motor. The motor is rotating, and when the motor is rotating, there is a theta out which is changing. The theta out is coming this way to a device, sensor, and then it's coming back to the comparator again. Now, what would the physical system look like? Okay, the physical system would look something like this. Okay, so this is my input. Let's say I'm giving a voltage as input. So I'm giving a voltage, and there is a potentiometer here. So by changing this position, I can change the voltage. That is, so this is my V. So I can change V by changing the position of this potentiometer, right? So this V is being multiplied by K, which is the amplifier gain, and then it's going to the DC motor. This DC motor, let's say, is connected to a turntable. Let's say I have a link like this, just for example. Okay, this is rotating about this axis. So if I increase the voltage, what will happen? The speed of the motor will increase. So the turntable will start rotating faster. And to check that speed, I'm connecting a tachometer there. Tachometer is a DC motor only. And the DC motor is giving, I'm connecting it here. So when the DC motor is rotating, what is happening? I'm getting voltage here. Okay, so this voltage is going back here. So this is my voltage out. Okay, and this is my voltage desired. Okay, so what is the present position? What is the present speed of this link is proportional to the voltage there now that is being generated in the tachometer. So if I want to increase the speed, what do? I increase the voltage here. I move the potentiometer such that this Vk is increased. If I want to decrease the speed, what do? I bring it down. Okay, I decrease what? I decrease the input voltage. So it's very easy to understand how this is working. So we have a motor which is connected to the turntable, or I can say there's a link. I can actually fix a link there. Okay, there's one link there. And the speed of the DC motor is connected to a tachometer, which is giving me the present speed. So this is a speed control experiment, let's say. So in the speed control experiment, we are controlling the speed by controlling the voltage that is coming to the DC motor. Okay. Now the corresponding diagram will look something like this. So desired speed is my input. The comparator is comparing plus minus there. The amplifier is the control device, and the DC motor is the actuator, and then the process is the turntable or the link. The feedback is the potentiometer. So from here to here, it's very easy to understand how do you make this block diagrams. So these are called block diagrams, and a block diagram basically is a control system representation of showing what is the desired input and what is the output, what is the controller, what is the actuator, what is the process, and what is the sensors. Okay, so this is a feedback control system diagram. Each of the elements you can correspondingly relate here. Okay, so this is my closed loop control system. Okay, now going back a little bit, in the car of autonomous cars, there's a lot of talk of autonomous cars these days. So how does the autonomous car function? It's a control system also. Okay, well, it's very simple. The car needs to track this the center of the road. Maybe it needs to keep its distance or follow this line at the center of the road. So it has to keep some distance there. So there will be sensors which will actually sense the position of the car. Maybe there is a camera or there is a LiDAR. So they can be LiDARs, okay, line lasers. So they will see what is the present position of the car in terms of its distance from the center line. So if it has come too close to the line, it will push it away. So this is my distance, let's say this is my distance there. So here I'm saying the desired distance is being given as input. I want this car to follow this line and keep a distance of d. Let's say it is 0.5 meters. Okay. Now there is a controller in there again. So what this one will do is it will take that, convert it into voltage and give it to the steering wheel motor. So probably it's an autonomous car. So the steering is connected to a motor, and by rotating the motor you can rotate the steering automatically. So if the car is keeping a distance of d from the line, it will just keep going straight like that. The moment the distance increases, what will happen is it will try and bring it this side, and if this distance decreases, it will try and move it that side. Okay, so if I draw the top view, this is my line. Okay, the car is here. Okay, so it is traveling like this. If this distance d decreases, it will move the car that side. If the distance d increases, it will move the car this side. So what will happen is, by just changing the theta of the motor, so what is happening is you are getting the car which is following not exactly straight as shown here. It is following the center line of the car. This is how an autonomous vehicle works. So what is the input? The input is the distance from the center line. What is desired? Maybe there is a distance that the car has to keep. And how is it doing that? It is basically finding the difference between desired minus the present, amplifying that, multiplying that with a gain, and then it is rotating the steering in a particular direction. Okay. Now, in terms of research, over the years, the evolution of control systems and robotics, especially control systems and robotics, has been, on one side we have autonomy. Okay, so autonomy is very, very high, and the other side is flexibility. Okay, so about 1960s we had NC machines and fixed automation, which has a lot of autonomy, but they are not flexible. That means you cannot keep changing their program and making them do different things. So 1970s we have robotics, which is coming in this region, and then the direction in which all these systems are improving is that there are improvements in sensors, vision, language, AI, and we are moving towards the direction of intelligent systems. Okay, and intelligent systems would mean that systems which can take decisions by themselves and they can listen to higher level commands, and that is the direction in which control systems has evolved over the years. So today we finished our part on actuators, and then we had a very brief introduction on control systems. Okay, very basic control systems. So from the next class we'll be looking at how to design very simple control systems like PD controllers, PID controllers, and then we'll start off with the position regulator. Then we'll move on to trajectory tracking. Okay, and we'll also look at things like stability theory. So we'll stop today. Thank you.